Good evening, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 25th problem from the Project Euler problem archive. So this problem asks us to find the index of the first Fibonacci number with at least 1,000 digits. And by index, it's just referring to this subscript here. So the first Fibonacci number has index 1, the second has index 2, etc. Now, this may seem like a very difficult problem if not for the fact that we just added addition to our big integer class in the last video in preparation for solving this problem. And so that will allow us to work with very large integers up to and including 1,000 digits. So let's get into it. As usual, we'll copy our template directory to make our problem directory. And we know that in this particular problem, we're going to need to use our big integer class. And so let's just change the makefile real quick to add our number theory library. And let's, before we start writing our solution, just jump on over to that class really quick. You'll recall in the last video, as I mentioned, we added these two methods here, which we'll be using. But we also need the ability to compare two big integers. And we have a the equals equals operator here, but we're going to need a little bit more than that. And while we're at it, if we add, say, the less than operator, we might as well add the rest also. And so we're going to do that first before solving our problem. Now, we could implement each of these operators individually, but that would be a little bit tedious. And so we're going to use a little helper function here called compare. So we're going to have this function called compare, returns an integer, and takes a constant big int reference. We'll call it n, and that will be const also. And the way this will work is it will return -1 if our big integer is less than n, 0 if they're equal, or 1 if our big integer is greater than n. And so then we can use this method to implement each of the comparison operators up here. So let's also list out the remainder of those operators. So we're going to need not equals, we'll need less than or equal to, greater than, and greater than or equal to. Okay, so now let's jump over to our source code. And we'll just add those right here. We will be replacing this existing implementation for the equals equals operator so that all of our operators will use our compare function. Okay, so have a big int operator, and we'll say if, actually we can just say return compare n less than 0. And all of the implementations are going to be very similar to this. So we're just going to copy and paste this 6 times. And one more. Okay, so we'll start off with equals equals, not equals, less than or equal to, greater than, and greater than or equal to. And now you can see why I've defined this compare function as I did, because it makes all of these operators very easy to implement. Okay, so now we just need to implement that compare function. And we're going to stick that down after our right cell method. So that should be at the very end down here. Okay, so we'll need an index. And we need to know what the maximum size is between these two big integers so that we can compare all of the cells. So we're going to say uint32t size is equal to, we'll make this constant, and we'll say max of cells.size and n.cells.size. And then we'll say for I is equal to size minus 1, I is greater than 0, and read cell I is equal to read cell, n dot read cell I minus minus I. So this is just going to find the first cell where the two big integers differ, starting with the most significant cell. If it gets to the first cell and it is found no differences, then we just need to examine that cell to determine which is greater or larger, or greater or smaller. Okay, so now we can say, let's see, uint32t, we'll call these this val and other val. And we'll say this val equals read cell I, and other val equals n dot read cell I. And then we'll say if this val is less than other val, return -1. Else if this val is greater than other val, return 1. Else return 0. Okay, so that should be all we need for the comparison code. Let's just make sure that that compiles and passes our existing tests. So we'll go to common, make, looks like that builds. We'll go to our tests, make, and looks like that passes. Okay, so now let's get into our solution. So go back to our main.cpp. We'll need to include big int.h. And we're going to want to have a big int, we'll call it 1,000 digits. And this is going to be the smallest number that has at least 1,000 digits. And so we can check to see if our Fibonacci number has 1,000 digits just by comparing against this number. And so we need to construct this. So we'll say we need an index, call it I. And you'll notice that the first number to have 1,000 digits is going to be 10 to the 999. not 10 to the 1,000th. You'll notice that the first number with 2 digits is 10 to the first. The first number with 3 digits is 10 squared. So you see that it's always off by 1. And so the first number with 1,000 digits is 10 to the 999. Okay, so now we're going to say for I is equal to 0, I is less than 111, and you'll see what I'm doing in just a moment here, plus I, and then we're going to say 1,000 digits dot multiply 1 billion. And so you'll notice that multiplying by 1 billion is going to add 9 zeros. Each time we need a total of 999 zeros, and so we're just going to call that 111 times for a total of 999 zeros. Okay, so that gives us our bound. Now we'll need some big integers to hold our Fibonacci numbers. So let's call them A and B. But now we want to be able to easily swap between our current Fibonacci number and our previous Fibonacci number without having to actually copy the contents of our big integers. And so to facilitate that, I'm going to create a pair of pointers. We're going to have curfib, and we'll start with that. Oh, I've made a mistake here. This should also be a 1. Curfib equals address of A, and big int prevfib equals address of B. So this is just going to point to the current Fibonacci number. This is going to point to the previous Fibonacci number. For now, these will have, these will correspond to index 1 and index 2, I believe. So yes, index 1 has value 1. Index 2 also has value 1. Okay, so we're going to say we want to say I is equal to 2 because we're going to start off by calculating. Yes, so at this point, our curfib is pointing to the Fibonacci number with index 2, and so that's going to be our invariant there. So we'll say for star curfib is less than 1,000 digits. We're going to, let's see, we want to swap the current and previous and add the new previous to the current. So we're going to say std swap big int pointer, and we're going to swap curfib and prevfib. So this is just what I was talking about, where it's much easier to swap 2 pointers than it is to swap the contents of 2 big integers. This is a very lightweight operation, and that's why I added this extra layer of indirection here. Okay, so now we just need to say star curfib, or excuse me, curfib points to add star prevfib. Okay, so that's going to add the previous Fibonacci to the current Fibonacci number to get the new current Fibonacci number. And then we'll also need to say plus I. Okay, so after we've finished going through the loop once, we will have calculated the third Fibonacci number and incremented I to be 3, and so that should all be correct. And then down here, we just need to say printf first fib number with 1,000 digits has index %u. Let's see, it seems like there's been a minor mistake here. Let's see, that should be... Oh, my mistake. That should be while, not for. Okay, and so it gives us the answer 4,782. Let's just jump over to the archive, and we'll see that that matches our answer. And so for the next video, I'm going to tackle this same problem, but using analysis alone. We actually don't even need to write any code in order to solve this problem if we're clever enough. So if that sounds interesting to you, please keep an eye out for that video.